all the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Hello, everybody. Thank you for coming to my talk. My name is Griswald Brooks. I'm a senior robotics engineer at Picnic Robotics, and I'm also the robotics chair here at CppCon. And I'm here to tell you a thing or two about mdspan. So, got to get this right out of the way. This is very much like I see in many of the talks. While mdspan was accepted into C++23, at the time that I was working on this project, I did not see that GCC actually supported all the features of mdspan. So while I stood for the entirety of this talk, I was using the Cocos library to implement all of this. The reference implementation of mdspan. So the thing that should be more or less exactly what's in the standard is what I was using, but it was not technically the standard. And then at the bottom there, right, is that GitHub link is going to be all the code if you want to go see it. All right, so got three main goals for everybody here today, right? I'm going to try to give you all a little bit deeper understanding of mdspan layouts and accessors. By the end of this talk, you should all know, or at least have a starting understanding of being able to implement your own layouts and accessors in mdspan. And I'm going to dispel a number of common myths and misconceptions about the restrictions of mdspan. I'm going to try to do this in three parts. So I'll briefly go over, a little bit of history, a little bit of motivation, why we have mdspan. Then we'll talk about the layout policy, right? We'll use that in the context of mobile-based navigation, robots driving around warehouses, sort of thing. We'll talk about the defaults, how to do your own layout policies, this thing called submaps, lasers, oh my. And then the last part of it, we'll do accessors, right? Talk about what accessors are for, what the default accessor does, and we'll use an accessor to get my robots to tell me if I have any beer. So let's go. mdspan. Now, I am not a historian, but Nevin Lieber is. So if you want to actually know like the history of mdspan, how it got started, how it got integrated in the standard, Nevin has a great talk from 2022 about that. And of course, I have to mention the two talks that really got me going on this project. One of them from Timur in 2022. He was actually the talk that really showed me wow, mdspan can do all these really cool things that I never would have thought of. And of course, Bryce, one of the authors of mdspan at CPP North, he gave a really good presentation about a lot of the intricacies of mdspan, stuff that I won't get to cover here. So a lot of it you should go for him because obviously he's the expert. And I have to give a shout out to Daisy Holman and Damien Lebrun-Grandi for helping me with this talk. So Daisy actually contributed a little bit of code to this talk, and Damien reviewed it for me, make sure I didn't mess up some of the policies. So first question, don't we kind of already have multi-dimensional arrays in C++? I mean, I can think of at least two different ways to do it, right? I can use a C-style two-dimensional array. I can use a vector of vectors, an array of arrays, right? That sort of thing should work, right? Well, yes, but I can think of at least two off the top of my head reasons why that's maybe not the best thing to do, right? So if you have a C-style array of arrays, yes, all of the memory is contiguous, but of course those are static dimensions because they're only at compile time. So if you were going to try I don't know, load an image, right, from a file, you wouldn't be able to use this technique. Another one, of course, would be doing a vector of vectors, right? So now you can do dynamic allocation, of course, but now the rows are actually no longer contiguous in memory, right? They're non-local, so you're going to have a little bit of performance hit there. And of course, because it's a vector, there isn't actually anything guaranteeing that each row is the same length. One could be a little bit longer, one could be shorter, and there's no mechanism out of the box to be able to help you with that. I seem to remember, though, that computers actually don't have two-dimensional RAM or three-dimensional RAM or four-dimensional RAM. My understanding is that they kind of store bits in like a linear progression, and we just kind of like, we're talking about a multidimensional data structure or like our programs in general, just kind of like map to those locations. We perceive how that data is laid out. So we could do that. And in fact, I bet you half of the engineers here who are roboticists have written this class, probably more than once, or knew a coworker who wrote this class, because this ends up being the standard thing to do if you know ROS2, NAV2, right? The occupancy grids, this is how it's implemented. So you might take a stood array and take the dimensions of n by m and allocate that entire n by n array, and then through the call operator, map the indices, right, to the right storage location. Obviously, you could do the same thing with vectors so that you have a dynamic allocation for the size and shape of your matrix. So that's great. We're done. We don't do anything. Though anyone who's actually worked with multi-dimensional data, they like to have a few more tools, right? They like to have reshape. So let's say I've got like this 2x3 matrix. What if I'd like to look at it as a 3x2 matrix? What if I'd like to look at it as a 1x6 matrix, right? What if I'd like to actually take my 1x6 matrix and just turn it into a pure 6-element thing, reduce the dimensionality? And of course, what if I want to look at every other element, right, of my matrix instead of taking all of them at once? There's a lot of code that we'd end up having to write. So clearly, the C++ needs a more flexible multidimensional view type, which is where mdspan comes in. So mdspan is that multidimensional view type that does not have restrictions on memory. Like the previous example of our hand-rolled code, it is a logical, not physical layout of the data, which is what I showed in the beginning with the int of ints or vector of vectors, right? So this means that reshaping doesn't take any allocation. If you want to like instantiate or copy mdspans, they're typically very cheap. And they have a couple of customization points via strategy. So here's where those customization points come in. This is the template declaration for mdspan. First off, the T, right? That's the element that your data kind of has, right? So you might have a mdspan of ints, of doubles, of position, XY coordinates, of sample joint states or particles, something like that. Probably not particles, you don't need it to be 2D. And then we have this parameter that mdspan calls extent with a T, not extends, which is the shape, right, of our data. It might be, the number of rows, the number of columns would be the way to think about it. So it describes the shape, or for how far the span extends in each dimension, right? The extents has a couple different parameters to it, right? First of them is the number of dimensions that there are. This is called the rank. The length of each one of those dimensions, and then the type used to represent that dimension. So a couple examples, right? First one might be, I'm going to describe some data that is 2x3, right? And I'm going to use a size t to represent those dimensions. So that means there are 2 elements in one dimension, and then 3 elements in the next dimension. Next one, I might have something that's 100 by 200 by 800, right? And I might want to use an integer to represent that because I'm going to do some sort of math with it, right? Those are 100 elements, 200 elements, and 800 elements. But those first 2 by mdspan are called static extents because we both defined the rank, so the number of dimensions, and the length of those dimensions at the same time. And the last one, right, is called dynamic extents, which means that we can specify the rank, but not the length of those dimensions, right? Here I'm using a double for 3. I haven't tried this yet, but I'm almost certain that this means I could get an mdspan to represent continuous 3-dimensional space. First customization point that we have here, the layout policy. So the layout policy is the thing that maps your multidimensional index to a storage location. So that's like the whole purpose. So imagine if we had like this linear piece of data, right? 9 elements here. And we were going to like perceive this data as, let's say, row major, right? A 3x3 matrix where we're kind of like putting the data across the top, going down the next row, 3, 3, right? Row major. Rows come first. Column major. another thing, math people like to represent their data with, right? You see the data goes down the column first before going to the next one and the next one, right? So that's kind of like the idea with layout, right? Even though the data is still this, one-dimensional thing potentially, we're going to interpret it as this multi-dimensional thing, and this is how it would map. Then the last one here is the accessor policy. An accessor is all about taking the offset from the layout and retrieving a value from a storage location. So here, this is kind of like the default implementation of the accessor. I'll actually show that in its entirety later in the presentation, but I just kind of removed a few things to make it simpler, right? You can see that it's using the brick operator here on the pointer to the ints, right? That comes in through the accessor and then just returning a reference to that value. Okay. So that kind of overview. Let's kind of go one step further into the layout policy. So to reiterate, layout policy maps multidimensional indices or one-dimensional indices to some storage location, right? There's a couple of default layouts that come with the standard. There's 3 as far as I know. There's layout right. So layout right is that row major kind of layout, and this is actually the default. If you don't specify a layout and you make it mdspan, you get layout right. This is what you would see in a C++ array. This is what you see in NumPy. This is how it comes by taking the indices, right, and multiplying, in this case, the first indice by the width of the data and returning that. The opposite of that, literally, is layout left, which is column major, right? Eigen, Fortran, MATLAB, they all use column major representation, right, going up and down. And here you can see taking the indices instead of multiplying by I, by the width, we're going to multiply J by the height. And then we come to the last one, which is called layout stride. Now, layout stride is different. Now, I'm just going to explain this to everybody because I didn't really have a good grasp of what stride is. So I'm going to give you what I've learned about what stride is. Stride is about spacing in between the pieces of your data. So before we were multiplying one of the indices by a width or height. Here, we're going to multiply both of the indices, but by these different S parameters, right? So get a little bit more concrete. Let's say we had this 2x4 view, window, little matrix, whatever you want to call it, that we kind of want to represent. And we want to represent in this larger memory space, right? If we were to look at that one-dimensional memory space, and we were to take the first parameter, S0. S0 is the number of elements in between elements, right? So x1 to x2, x2 to x3, xn plus 1 to xn plus 2, right? That's that first stride parameter. Whereas the second stride parameter, S1, is the spacing between rows, or that grouping along the first dimension, the first extent, right? For example, if we were to have a 8x4 matrix that we're going to have that little window placed into, right? And we had that stride parameter of 1 and the width of that matrix, 8, right? Then we'd get that first example. So the elements, there's one element in between elements. That just means they go next to each other. If it was 0, which I did when I was first trying to do this, they'll just get piled on top of each other, which isn't very helpful. By contrast, in the next example, if we increase that stride parameter to 2, now we've got the spacing between elements, but you can see we still go down the same number of elements to get to the row. In contrast, if we go to the 1x16 one, right, now the elements are next to each other, but we've stepped down a row, right? And then I've made the choice, right, to say that the strides are going to be some integer multiple of the parent data, but there's nothing that says that has to be. So if I was to choose some non-integer number like 6, not a multiple of 8, you can see that the elements are next to each other, and then we from the first one, 1, 2, 3, 4, 5, 6, get to the next row. I think a really cool intuitive example of why this is useful is downsampling an image. So you can imagine if you were going to take some sort of strided view, and you were going to skip every element and skip every row, right? And I was going to take like some high resolution image and pass it to, I don't know, some machine learning pipeline that needs a particular like resolution of that. I could do that. Another like probably obvious example to people who aren't me is like most images are in color, and color is represented by 3 to 4 numbers, not just one. And so you might have that all in your, your image, and you might be skipping every third or fourth to just get the red pixels, or just get the green pixels, or just get the alpha channel, right? So kind of like pretty obvious implementation of stride. All right, so those are the defaults. Those are what come out of the box. Now I'm going to talk a little bit about what it would take to do your own custom layout. So there's a couple of requirements for making your own custom layout. Whenever you make a custom layout policy, what you're really doing is you're making this object that has another object inside of it. So your layout has an object called mapping. And the mapping struct has to have a templated extents parameter. Now, you don't have to use this for anything other than when you return a method called extents telling you about the shape, right? How big your data is. Well, not the shape, how wide, not how big your data is, how wide, how long. The shape of your data, not how big it is. You have to have that template parameter. But then you have to have this collection of other operators, which I've grouped together a little bit. So the first one, yay, this is the fun one. This is the one that we're all here to do, right? We've got our indices, and we want to do some mathemagic to it and like get some location that we're going to map to. So this is the call operator, right? The call operator can have as many dimensions as you want, or as few as you want. You can have your call operator take, a expanded number of indices, or you can restrict it to just 1 or 2. Required span size. So this is why I corrected myself a second ago about saying this isn't about how big the data is, extents is the dimension, right? When we talk about required span size, let's talk again about like that our layout is inside some other piece of data, right? So if we had that strided example again, where we just space out, the individual elements, then to represent 8 elements, we actually need 15 locations to do so, right? So our required span size has to be 15 to represent this strided 2x4. Okay, uniqueness. So uniqueness asks the question, does every index in your layout map exactly to one storage location? Now, this isn't always the case. For example, in Timur, in his talk, he showed how to implement a upper triangular matrix, right? Upper triangular matrix, for those of you who aren't dipped in math, right, is that you have this, matrix of numbers, and they'll be symmetric around the diagonal, right? So the elements at the top will be the same as the elements at the bottom. Diagonal's unique, of course. So you don't actually need, n by m number of elements to represent that. You can do a little bit more than half of that and still get the same representation. But in order for that to be the case, your multidimensional indices now need to map to 2 locations in some instances, right? So not unique. Exhaustive. Going back to that strided example. In the kind of like bigger space, there are some storage locations that your indices will never get to, right? So if you're doing a normal matrix, then every index would map to every storage location and would be exhaustive. But in the strided layout, it's not. And then strided. Like, why do we need another method to ask if something is strided? We just went over exhaustive, right? Well, the thing is that strided is about whether or not there's a constant offset between dimensions, right? So you can have a non-exhaustive layout, but not have a constant offset between dimensions. And so we'll see an example of that later. The things I didn't say. I went over these requirements. I did not say that the layout required default constructibility. I did not say that the layout was required to be stateless. I did not say that, I don't know how you would measure symbol computation, but you could compute anything you wanted inside a layout. And then, of course, we went over the uniqueness and fullness of the mapping. I'm pretty sure, though, I'm not just at CppCon, but I'm in the robotics track, and I haven't said anything about robots yet. So let's talk about robots. In my field, right, mobile-based navigation, we have like a logistics robot going around a warehouse, we usually make a map of that warehouse, right? So that the robot can path plan and localize and navigate through that. And one common representation is something called the occupancy grid. So the occupancy grid is going to look like a bunch of pixels where if the pixels are white, then we say that there's no obstacle there. If the pixels are black, we're going to say obstacle, bad thing, don't run into it, or reference off of it. And then gray, we're going to use to say like, oh, we don't know the state of that particular pixel, right? So here's how to use an mdspan to represent an occupancy grid. Super easy, definitely the base case, right? So first, parameter that we're going to have here, right? The shape is going to be the extents, right? The dimensions of our data. In this case, because we don't know exactly how big the map we're going to load is, right? It might be like my little lab. It might be an acre of a warehouse, right? So that's dynamic, but we know it's going to be 2. So we're going to say it's going to be 2. And we're going to use, in this case, a vector to store the actual data, to own the data, and the mdspan to just view into that storage, right? So we need to get both of them the shape. And we're going to fill up the thing with some value here, gray. Gray is going to be what I fill it up with because I don't know anything about anything. And then we're going to give the mdspan, right, that vector to refer to. And then throughout the rest of the code, we'll use that mdspan to operate the data. Cool. That was pretty easy. Talk done. As I said, a lot of times the warehouse or whatever space we're in, that could be really big. As I was not joking when I said it could literally just be an acre, right? I think like the gigafactory is like several acres or something crazy like that. Probably doesn't even fit. So typically when we're doing some sort of, maybe we're doing path planning, maybe we need to use a big chunk of the map, but after we've planned the path, we usually do some sort of local planning, some checking, some control, some obstacle avoidance, right? And so we'll take like a constrained little piece of the map, right? For the purposes of this talk, I'm going to call that a submap. You might hear me use another term, but I'm going to try to stick to submap for this. So it's just a smaller region, usually centered on top of the robot that we're following, and axis aligned with the bigger map. So how would we get a submap? Well, let's go to our handy friend, layout right. Should be pretty straightforward. That's how we get a piece of dimension, right? So we're gonna, take the shape, right? We're gonna, 10 by 10 little window. Get the place we want it, upper left-hand corner somewhere in the bigger map. Get that extent. Come up with that row and column. Advance the pointer so we're at the first spot. Make our layout. Give it the shape. Should be great. That doesn't look like a square to me. I feel like there's square things about it, but it's not quite a square. Something went wrong. Well, when we gave it the shape, right, and we were building this mdspan that's of layout right, what we're saying is that when we use the span, we treat the span as if it is this 10 by 10. But it says nothing about how the underlying data is going to map to those things, right? So just like how when we made the occupancy grid, that was a one-dimensional thing, here when we're making that layout, passing this pointer, I guess that's going to be one-dimensional too, but we'll just view the thing as a 10 by 10. And that's not what we want here, right? We want to actually like get that little chunk of the map. So what do? Hey, we have a way to specify how far the data should go in between each other, right? So as I said before, right, there's the first element and then there's how many for the row. So if we create a stride, we're going to say, hey, each pixel should be next to each other, but every time we advance, in the next dimension, we're going to skip an entire row here, saying like the extent, which is the width of, the big occupancy grid. And then we'll do the thing again, we're upper left-hand corner, pointer, here you go. Boom, now we actually have our little square. Feels great. This is such an obvious and useful thing to do that mdspan just has like a function to do it. It's called submdspan. You don't have to mess around with those things directly. If you just make a tuple that has like the first row of the index first index of the row and column, and the last index of the row and column, you just give that to the mdspan, it'll just spit out the same thing. Use it, it's a lot easier. Okay, so we have our submaps. But I have a problem with submaps. So if you've used a particular open source software to do robot navigation, you might notice the thing called submaps, as I said, is axis aligned, right, with the bigger map, right? But the robot's in the center, and the robot turns, it like moves as it's driving around, it changes its orientation, which means that within that submap, the number of pixels for it to plan with is changing, right? So like you don't have a constant distance actually that you get to plan. So if you like make a turn, then that's reduced. Now maybe your plan can't extend that far. Maybe you can't do that obstacle checking while you're there. And I just kind of like think it makes it a little bit less deterministic because it makes it dependent on orientation. So what I'd really like to have is a rotated submap. A submap whose orientation is always aligned with the direction of the robot. How do we do that? Well, so far we've only talked about how to get square-ish things out. And that seems like all the tools that they've given us. So now it's time to write our own layout policy. Yeah. Okay. So here we're going to have that template argument on the extents. But notice, in this case, I'm saying this only works for 2D, right? We're not going to have a 1D or 3D rotatable for the occupancy grids, right? We're just going to have 2D, so throw that requires on there. Obviously, we need to tell the layout something about the dimensionality of the parent, the shape of the parent. We need to tell it something about the shape of the window we want to make. Notice here, we're doing that through the constructor, right? Layouts do not have to be default constructible. We can give it as many parameters that we want. And then, of course, we have to tell it where to put that map, right? So the pixel that we want to center on my implementation, it's upper left-hand corner, but should be center on, and then the rotation, right, that we're going to have there. Now, this is a little bit of a technical detail, but I think it's a pretty important one. As we talked about required span size, before with the squareness, it was kind of obvious how much span that you need, but now that we're rotating it, now we are going to need more pixels in the parent than we do in the view that we have itself. So in order to solve this case, right, we're just going to run the call operator a bunch of times with all of the indices that we could have and get the last storage location +1 and return that. I feel like that there's like a cheaper way to do this, but for this talk, this is what I ended up doing, and it worked. We're going to store the shape of the parent, shape of the span, those translations and rotations in the layout itself. Hey, layouts can have state. There's nothing that says that layouts have to be stateless. In this case, that all came through the constructor, but I can imagine a scenario where we do the access operator and we keep updating the state of the layout, right? So layouts can have state. And then we get to do the actual call operator. Now, this is way too much detail for the point that I'm going to make, but I'm just going to take a little bit of my time back and tell you about a cool algorithm I learned about while I was doing this talk. So I don't know if any of you have tried to rotate a matrix, a picture, or something like that, but what happens if you use the normal transform is you get all these holes, and you get all these extra pixels, right? Because as you're doing that mapping, that's supposed to be continuous, but then it's discrete. So you don't always land in a place in the parent grid. In fact, when they do this with images, like images that you look at, what they'll actually do is look at the destination, and they'll sample back to the original, the source data, and just kind of like average those pixels together and land them there. I don't want to do that, right? Because I said, I've got a black pixel, that means occupancy, bad, don't go through there, right? And a white pixel means clear, good. Now, what if I'm doing sampling and averaging those two? I'll get unknown, right? I don't want to do that. I need a unique mapping from one pixel to another pixel. And I don't know if any of you guys watch this thing called YouTube. There's like a couple people in this room who are on YouTube, but there's this comedian, this this mathematics comedian called Matt Parker, right? And I watch his stuff all the time. And I watched an episode of his where he described this algorithm called the 3-skew algorithm, which actually uniquely rotates a set of pixels by shifting them 3 times. This is like a mathematical equivalency. It's a formula that says that 3 skews are equivalent to any 1 rotation. They used to use this in Nintendo games. So when we only had like a few pixels, right, they would use this algorithm to shift things around. So this is that algorithm. It's not something you have to like read in detail. I just thought it was really cool. So just to highlight the point that I was saying again about the requirements, if we were to have a rotated submap here, we can see that all of the indices will map to a storage location. But obviously, we're not using all of the data in the storage location, so it's not exhaustive. And it doesn't have a consistent spacing between elements, right? So like initially it's 4, then 3, then 2, then none, and then 1, and then 2, and then 3, and 4 again, right? So not exhaustive, but also not strided. So what do we get? We get this. So let's say we had one of our rotated submaps in our parent map, and I'm going to take this little square on the left and paint it black so that you can see what I'm talking about. And on the right, this is what the robot ends up seeing. You can kind of see where that corner was on the left side of the image and where like the laser scan lines are coming through in some of those unknown space. So great, now we've rotated some maps. I'm happy. I think I just said something about lasers. Lasers. So we're going to now talk about how to get layouts to be non-square. We're going to talk about more state in the layout, and we're actually going to talk about dimensionality reduction. Lasers, for those of the uninitiated. So if we have this like blue box, right, we're going to use lasers to take range measurements. So we have this blue box that's supposed to be a laser, and it fires out this photon, and it hits like this brick wall, right? We can measure the distance that that photon took to hit that brick wall. What does that look like in the occupancy grid? So if we had our gray unknown occupancy grid, from the place of the laser, we're going to clear out all the pixels up until we get to the brick wall. When we hit the brick wall, we're going to place a black pixel, right? Occupied. Something's there. But we know if we hit the black pixel, nothing was there in between, right? So we're going to clear it out, then set it. In my field, the way that they do this is they take that laser and they spin it around really fast. Honestly, they take a mirror and they spin the mirror and they shoot the laser up, but they spin it around really fast, take like 900 measurements at 15 hertz, like a 270-degree range, and we'll get a scan of the room. Laser scan. So laser scan has 2 parts, right? That occupied part, the part where we set pixels, and then the part where we clear pixels. Let's talk about setting of the pixels. So we're going to mark the ranges, I called it the vertices, right, that we got back from the laser. In this case, we kind of lost the ability to talk about the data in a 2-dimensional sense, right? Even though the data is in a 2-dimensional grid, we can't really like say, give me coordinate x, y of the laser scan, right? It's going to be somewhere else. If we knew coordinate x, y, well, we would just be using the laser scan, right? But we can talk about how we would progress through the laser scan in a 1-dimensional way. So layout, vertices, give it the vertices, take them, transform them into the space that we want. And then here, because the laser points, they could hit some of the same points, and we want to make sure that the mapping is unique, we're just going to stuff all that into a set and then pop it back out as a vector. And this makes the call operator super, super simple, right? Because we're just going to iterate through the 1 to n number of elements. We're going to take the coordinate that we stored in the vertices list. We're going to transform that back into the strided layout, and we have our offset. And this is how we're going to use that data. So here, we're going to have that 1-dimensional extent that I talked about for the mdspan. And we're going to create our mapping, right? Using that 1D extent, we're going to call that our scan. We're going to use the extents of the map and the endpoints that we got from the scan, and then we're going to return our vertices view, right? And this is what we get if the robot for some reason was in a cylinder. But this is what we get. You can see where all the vertices land in the map. Okay, ray tracing, gonna be very similar, right? Different mapping type, right? Gonna do the coordinate transform, except in this case we're gonna use Bresenham's algorithm to actually do a ray trace from the point in the middle to the endpoint that we're going. Uniquify it, vectorize it, boom. Exactly the same call operator. No difference call operator because we're just iterating through a vector at this point. Okay, so now we have lasers in our map. Awesome, super exciting. What about the robot? So if I have a mobile base and it's driving around, we tend to look down, right, at where the robot is and kind of like draw a shape around the robot so it doesn't get too close to anything. We call that the footprint of the robot, right? We usually represent the footprint of the robot as like a polygon. So polygon, right? We're going to take that because we're going to like put the robot into the map, or more likely, we're going to use the shape of the robot in the map to do planning, right? We're going to like say, what if the robot was here? What if the robot was here? What if the robot was here? Will it collide with anything? Check all those pixels. Yes, no, collision checking. So we're going to take those vertices, right, that define the polygon of the robot, transform them, and then this time, instead of doing a ray trace, we're going to do a convex fill, which is basically the Bresenham ray trace. Then we're going to take all the pixels in the middle and fill them in. And this is what we get. We get our nice little non-square robot driving around our map. That was a lot. At least for me, that was a lot. So what did we get out of that? We learned what a layout is and what the requirements for a layout are. We explored a bunch of the built-in layouts, right? We learned how to make our own custom layouts. We discussed statefulness. We discussed non-default constructors. We discussed dimensionality reduction. I have a question. So that whole time we were referring to a stood vector, right? So that was on the heap. But what if our data isn't on the stack or the heap? Let's talk about the accessor. So the accessor policy is the thing that takes the mapping, right, the offset from the layout, and then uses that to get the value, right? Earlier in the presentation, I told you I would show what the default accessor looks like from the standard. This minus a couple of slideware lines is exactly just copy and pasted from the Cocos library. So, couple important types to talk about here. Now, this class is templated, but that is just a choice that they made, unlike the layout. No need for it to actually be templated. But it's three important types we need to talk about. First one, element type, right? Element type matches the element type of the mdspan. Reference. Reference type matches what's returned by the Brooks operator of the mdspan. Data handle type. Data handle type is the first parameter to the constructor of the mdspan. And then here you can see the accessor, right? Taking the data handle type, Brooks operator, returning that reference. One more time. The element type matches the element type of the mdspan, which is also the first type template parameter. The reference is returned by the Brooks operator of mdspan. The data handle type is the first parameter of the constructor of the mdspan. Those things are all true. What did I not say? I did not say that the element type, the reference type, and the data handle type have to have any relationship to each other whatsoever. So in the default accessor, yes, you have element type as a thing, and then reference operator, and then pointer operator. None of that is true. You do not have to have that at all. You don't have to have any template parameters if you don't want to. You don't have to have it be default constructible. You don't have to have the memory to be contiguous. You don't have to refer to memory at all. Why would you do that? All right, so let's talk about a Hilbert matrix. I have no idea what a Hilbert matrix is. I looked this thing up on Wikipedia. It is not a Hilbert curve. That's a different thing, right? I tried to figure out what this was used for, and I used to be okay at math, and then they immediately dived into deep linear algebra that I couldn't figure out. So it's being used in this example because a Hilbert matrix is a matrix whose values are completely dependent on the indices. So whatever the indices are, uniquely determine, or not uniquely, right, because it's a symmetric matrix, what the values are. So you can see the elements there, right, 1 over I plus j minus 1. That's what a Hilbert matrix is. Well, we already know the indices, right? And so we can write our own Hilbert accessor. Yay! Note here the reference type doesn't seem to be a reference type, right? It's just the value type. If you tried to put a reference type here, you'd actually get a compilation error called return reference to temporary. For the data handle type here, instead of it having anything to do with double, I put a std function there just for the lulz. And the accessor will call the std function with the offset that we got from the layout, and then we're going to give it the width parameter of the Hilbert matrix. And then this is the Hilbert function, right, that we're going to use. That's going to be what gets populated in that std function. I know it doesn't quite look like the formula I showed before, but trust me, they're equivalent. And then we can use it. So we can make our mdspan Hilbert view, right, with the 3x3 extents, and we have to specify layout right here because we need to specify the accessor. So then you have to tell it what the layout is. And we're going to tell the Hilbert accessor that it's going to be a width of 3. We give it that Hilbert function we made. And now when we access the elements of the Hilbert matrix, boom, we get the values we're supposed to get. No memory of any kind. Pure functional mdspan. So the reason that this sort of thing was done by the designers is because when they were making this, they were doing a lot of GPU operations. So they actually weren't doing anything with the stack or the heap, but they're manipulating, matrices on the GPU, and they needed to be able to call into that, right, without having to do all the special CUDA calls that you normally have to do. Okay, back to robots. Roboticists have this just thing that they always have a problem with, is they never have enough beer. Just like ever. You can see all these examples of roboticists spending days and weeks and months of their life just trying to get the robot to give them beer, right? But I pose a question. Why would you do that if you didn't know if you had a beer, right? You probably need that as a prerequisite before going to get the beer. So where's the beer? Here's what we're going to do. We're going to have a 2x3 layout, 2x3 container, not on stack memory, not on the heap, not on the GPU, but we're going to have table memory right here, right? Have our 2x3 matrix. We're going to have our accessor here, right? Actually, when it gets a request for the value of that 2x3 matrix, the accessor is going to go out to that storage location and use its IR sensor, right, and check to see whether or not there's a value in the storage location. All right, so how do we do that? So here's our bin checker accessor policy. This is the whole thing. Again, if you go to that spanny GitHub, right, you can see this is the entire thing for this accessor policy. The robot is talked to through a serial port. So not only could there be a beer or not be a beer, but the serial port could be disconnected or my computer could be on fire. So I kind of like using an expected where I can. So the element type here is going to be an expected instead of just the bin state. Our reference, again, is just going to be the value type. No need to use an ampersand here. Because I'm telling the robot about the position, like the literal metric position in meters of the beers through a JSON file that I store, I am using a data handle as this position T type thing that I read in. The original version of this had no such thing, and the robot arm was actually the data handle type. You can see that in my lightning talk last year. That's how we did it. So here, right, we're gonna have the accessor policy take the arbiter. I'm calling it the arbiter because robot arm made sense when there was one, and then later you have to plan between them. And so the arbiter, right, is going to handle the robot arm. So that gets passed into the accessor, no default constructor, right? And then here, the accessor is just gonna grab that goal, right, that somebody gave it, that bin offset that somebody gave it, get that goal, and then give it to the robot arm to get the value. Ah, yes, okay. Element type, value type, not related to data handle type, passed in through the accessor, or to the access function. Not a reference type, returned from access. Okay, synced up again. So here's how we're gonna make that mdspan. So just to drive it home for this example, that first element of the template is the element type of the accessor. And then we're gonna have a 2x3 matrix. Not discussed here, but discussed in my lightning talk. We're gonna use a bounds checked layout policy that Daisy had written for me, which basically a compile time checks the dimensions that you're checking, make sure you're not going out of bounds. But then we give it the accessor type for our bin checker. And then this is how we use it. So JSON file to read the literal metric positions of the beers. And then we have to do this inverse kinematics modeling thing about what the robot arm looks like or something. Then we're gonna have the bin checker accessor policy created with that arbiter. And then we're gonna create that view. So we're gonna combine the locations of the beers and the thing that's gonna check the beers. And then we'll just iterate through the rows and columns and have the robot arm get the bins, the values of the bins. And of course, to give you an exhaustive discussion about how the robot arm is commanded with the arbiter to read in all the bin positions and then take the inverse kinematics of where the arms goes and interpolate the path from where the robot is to the position of the beer. Just read the code. It's really long. There's a lot of planning stuff in there. Just read the code. I'm sorry. Sorry to do that. Okay. Does it work? Okay, well, it moved anyway. All right, I thought, though, that went really good. The robot arm went to each beer location and checked in on the beer location. It did kind of seem to take a long time. It was pretty quiet up here while it was just kind of moving around. And we have 2 arms. So couldn't we have both arms check on the beer? I think that would be really cool. So that's what we're gonna do. We're gonna have the same whole layout there, same 2x3 matrix, but instead of having just one arm doing all the checking, we have both arms doing the checking. The code was so simple that I didn't have to change the accessor policy at all. I had to make a new arbiter, right, to deal with 2 robot arms, but didn't have to change the accessor. It just worked right away. All right, let's try that. Agreed. All right, that kind of sucked. Still took the same amount of time, nay, probably longer, right? Probably because, and this is the thing that we kind of forget, is when we're doing that access, right? We access the one element of the array, we wait for the value. We access the next element of the array, wait for the value. And when that's done in the order of nanoseconds, yeah, it's not really something we think about. Well, it takes whole seconds those values to come back, that's kind of tedious. It's kind of like we need the arms to operate like at the same time, like instead of synchronously, like asynchronously. Let's do that. So here was that Accessor policy before, right? Looking at the reference type, it's just the same as our element type. Let's make one change. Let's make that a future. All we had to do was make that a future. We didn't have to change anything else about the Accessor policy. Again, doesn't have to be a reference type unless you consider future a reference, which you could. It's also a monad. But we just make that change, and now we have an asynchronous Accessor type. I did feel a little bit obligated to tell you a little bit about the arbiter on this one because it was a little bit more involved. So, I have the result type, which is that stood expected before. And what I'm going to do is I'm going to give it to a bunch of package tasks. So I have this package task type that takes the types of this bin occupied thing, where it actually checks the robot arm, talks to the serial port. And then in the call operator, we're going to spin up these package tasks, and then that's the things that's going to set the future. And then we're going to have these J threads that actually operate the two robot arms. One of the J threads is going to keep checking this thread safe queue, right? And take the list of goals that it thinks that it could do and then match those up. And if one of those things is there, then it's going to give it to the package task. When that's done, that's going to set the future. So not so much work on the Accessor. Yeah, a little bit of work on the robot side. But this is how we use it. So just like before, we're going to make our arbiter, tell it about the robot arms it has to operate. In this case, we're going to tell it about the actual positions of the grid because we need to plan between them so the robot arms don't hit each other. Going to make that async Accessor, give it the bin data, give it the mdspan, give it the bin data, give it the accessors, right? And then we're just going to iterate through the mdspan, get all those futures back. Get those futures back, right? Then we'll check on them. And if any of them become ready, we'll print their value and then just get rid of that because we're done with that future. All right, here we go. This should go perfectly. Yay! Thank you. All right, so let's wrap it up. What did we talk about? We talked about what mdspan is. We talked about the motivations for having an mdspan. We talked about the customization points, what layout policies and Accessor policies are. We talked about what the built-in options for all those things are: layout right, left, stride, sub-mdspan, the default Accessor. We talked about how to implement our own custom layout and Accessor policies, and we showed you that they're actually they can leverage all the flexibility that C++ can bring to bear. Whether or not that's always a good idea, whether or not you should build a couple of robots to implement a futures matrix type, not the point of this talk, but you can. All right, so as I've been saying the entire thing, if you want to go look at the code, this is my GitHub repo for this. And if you wanted to print your own spanny, I will put the 3D files on printables. It's probably going to take me a couple of weeks because I also need to design electronics boards for this. My wife actually, hi Tamari, she actually soldered all the electronics inside my robot many sleepless nights with me. So that's it. Any questions? Looks like we've got about 7 minutes.
Great presentation. I'm glad that we detected whether there were any beers or not. That was perfectly. You said that you used a Matt Parker video to do your rotations.
Correct.
I was wondering if you could use mdspan to model a Parker square and what that would look like.
I get the joke. I don't remember what a Parker square's shape is, though.
I think the answer is no. But
no? Okay.
You're
all right.
welcome.
All right, challenge Matt Parker. Make an mdspan for a Parker square. All right. Anybody else? Yes.
Hi.
Hey.
Great talk. That was a really fantastic
Thank you.
examples of custom accessors. And I'm working on an article now for custom accessor examples, and And so I'd love to refer to this talk in that article. I hope that's okay.
Great, yeah, and we can talk later if you want any details about where to find things.
Yeah, I posted some notes about minor details in the CppCon Discord, but
Okay.
I just wanted to point out about GPU accessor is the example that you pointed out.
Yes.
So the GPU accessor, the only difference between it and default accessor is that the access function is blessed with the device.
Is this a question?
This is a statement.
Okay.
So the only difference between the GPU accessor, which is non-standard access, and default accessor access, which is standard, is that the access function has device marker on it. So otherwise, it's just accessing memory.
Right.
And so the point of that is to protect you from errors at compile time.
Okay.
But if you wanted to do something more like what you were alluding to, there are accessors that one could write that do MPI one-sided or SHMEM, like remote memory puts and gets.
Yep.
And when you say things like go out and get, that's kind of what that would be. So one could write an accessor that does that.
That's what I should do for my next talk. I should refactor ROS messages to use shared memory through mdspan. It'll be perfect.
So great talk. Thank you.
Thank you.
Hi, thanks for the talk.
Hey.
Our use case is mostly with image processing. So this was really interesting to see how you can make custom accessors and all that. So appreciate that. I was just curious, do you know much about like the performance of or like things to be aware of with a custom accessor? Like is it evaluated lazily or?
Oh, no,
definitely
definitely not.
Okay.
Definitely not lazily, right? Like as you, I mean, just those are very normal functions, right? Like that didn't inherit from anything, my accessors, right? So those are just the structs that you would have, and so you do the call, and the call comes back. It's not ranges object. It's not a coroutine.
I see. Okay.
Right? I mean, maybe you can add those features to it. I don't. Isn't like click where you would do a yield on an accessor, but maybe by next year it will.
Yeah, I don't know off the top of my head.
Yeah.
I was just curious. Yeah.
Huh? Co-weight accessor. All right.
So obviously this is much more flexible than something like an eigen vector or an eigenmatrix. Are there performance considerations there with it? And obviously the point of this talk was to demonstrate cool C++ and cool robotics, but would there be applications where this could be more performant than an equivalent eigen use case?
I don't know. I imagine that what's actually happening when you're doing an eigenmatrix, right, is figuring out like the BLOS and LPACK calls to it. So like I know that I had a friend, for example, on my first job, and he was re-implementing PCL because his boss told him to. And like we ran into a whole bunch of like our own issues with memory alignment. We would have like this crash 1 out of every 1,000 times we ran the thing. I can't imagine that you'd get any like inherent efficiencies from doing that. But kind of like the thing that I like about mdspan for something I might actually use is it feels odd to me to take an eigenmatrix and put an occupancy grid into it, right? Like I'm sure that when they work on the linear algebra standard that mdspan will probably feature in the use case. I don't know for sure, I'm just speculating because it's a multidimensional type that just is in the standard. But it was really frustrating for me to have to like roll those classes my own to like do the navigation use case, right? And like I do plan as like a stretch goal to implement more and more of the nav stack and actually how cost maps operate, just to like get my hands dirty using this technique. So like in that case, right, you imagine the accessors actually peering through like the multiple layers of the the cost map stack, right? And it's not like I'm doing lots of matrix multiplications, but I do still have square data that maybe I want to run a kernel over, right? Maybe I want to like, expand, right, each one of the obstacles using my kernel function, something like that.
Sure.
Yeah.
Cool. Thank you.
Thanks. All right. Thanks, everybody.